In the earlier lectures, we had explored various numerical methods for calculating integrals. We had looked at various algorithms as well as ways of implementing them, both using NumPy as well as by using specialized functions available in the scipy.integrate module. In this lecture, we are going to take a look at a class of integrals which are called improper integrals. These are integrals which, strictly speaking, cannot be defined directly in terms of the standard theory of integration. An integral is called improper if either the integrand becomes infinite in the interval of integration, including perhaps at the endpoints, or the interval of integration is unbounded. So, instead of being from over a finite interval from a to b for finite a and b, it is over either a semi-infinite interval or an infinite interval, maybe the whole of real line. So, as an example, the integral 0 to 2 x by square root of 4 minus x square dx is improper because the integrand x by square root of 4 minus x square diverges at the endpoint x equal to 2. One more example, this integral x by 1 minus x dx integrated from 0 to 2 is improper because the integrand diverges at 1, which is somewhere in the interval of integration. Well, this is a very familiar integral. I am pretty sure most of you know the value, but this integral is also technically improper because the interval over which the integral is being done, 0 to infinity, is an unbounded interval. If you remember, the way in which you defined the integral, at least the Riemann integral, was that you took the interval and you broke it up into large but finite number of pieces, and then you took the limit in which even the largest piece went to 0. It is obvious that you cannot do such a thing if you have an infinite interval. You cannot break it up into a large but finite number of pieces and then take a limit in which the largest piece would go to 0. So, these integrals have to be defined somewhat differently. Well, just one more example. This is improper both because the interval is unbounded, 0 to infinity, and because the integrand diverges at x equal to 1, which is somewhere inside the interval of integration. Now, how do you define such improper integrals? In the mathematical sense, the standard Riemann or Lebesgue definitions for the integral do not really work for improper integrals. As I just said, you cannot break up an infinitely big interval into pieces and finite number of pieces and then take the limit in which the largest piece goes to 0 by just increasing the number of intervals. Also, if the function, the integrand, is unbounded somewhere in the region of integration, then the sum that you are supposed to calculate, whose limit is going to give you these integrals, would typically not exist. Now, the following are ways in which you can define the improper integrals mathematically. You could use one of these limits or maybe combination of these limits. You could talk of a limit in which the upper limit b, though taken to be finite, you calculate it with a finite b and then you take the limit as b goes to infinity. Of course, calculating this with a finite b makes this fall within the domain of the standard definition of Riemann or Lebesgue integration, and then if the limit exists, then things are fine. It could also be that the lower limit a is taken to the limit minus infinity. A similar point. Well, it could very well be that at some point b inside the interval you have a problem. So, what you do is you instead of integrating from a to b, you integrate from a to c and take the limit as c goes to b from the lower side. Or you have a problem with the lower limit a, and then you take this limit. This is a slight typo here. This should have been the other way around. Anyway, the basic idea is that you can take limits of otherwise well defined integrals and then calculate. If those limits exist, then the improper integral exists. Of course, These limits may not exist, in which case the improper integral frankly does not exist. So for example, this limit 0 to 2, this integral from 0 to 2 of x by 1 minus ax would be defined as the 0 to a integral, where a will approach 1 from below. Remember, 1 is the point where this integrand diverges, where you have a problem, and also integrate this from b to 2, where b would approach 1 from above. Now, of course, if you just did it without taking the limits, this integral from 0 to a and the integral from b to 2 would not really be the integral from 0 to 2, because it would miss the contribution from the a to b interval. By taking these limits, provided these limits exist, you end up with the result, which is the value of the improper integral. Of course, the limit may very well not exist in this case, and in fact I'm pretty sure it doesn't. So in this case the improper integral may not exist. But whether they exist or not, unfortunately taking limits is not really what you can do in a numerical computation. So how do we numerically handle things like this? An integral of f of x dx, where the integrand f we assume is otherwise perfectly well defined everywhere, but the integration limits are over the entire real line from minus infinity to plus infinity. So how do we numerically handle a case like this? Well, if the integral exists at all, then the integrand must die out pretty rapidly as x becomes very large, because otherwise you will get bigger and bigger contributions as you go further and further away, and that might lead to the integral not existing. So if this is the case really, then what we can do is you can numerically evaluate not this integral, but the integral from minus L to plus L, and then take larger and larger values of L. Now once the integral for begins to become insensitive to changing L any further, you would have reached the limit that you want. So this is a crude way, but it's often very effective. By the way, those of you who are mathematically minded might recognize that we are not really taking the limit properly here. That is, you are supposed to really take minus L1 to plus L2 integration, where L1 and L2 are two independent parameters, and take the limit as both L1 and L2 go to infinity separately. Here we are actually finding something called the Cauchy principal value of the integral, where the two limits, upper and lower limits, are taken to be symmetrical, and then you take the limit as L goes to infinity. It so turns out that if the improper integral exists, then the Cauchy principal value will have to be equal to it. If there are some cases when the Cauchy principal value may exist even though the integral doesn't. In many practical applications, the Cauchy principal value is what you really need. So we are not going to really distinguish between the Cauchy principal value and the actual integral, at least not in the rest of this lecture. Now, although that method was crude but effective, sometimes it pays off to be a bit more clever. So what you do is you choose two numbers a and b, both positive, and you break up your domain of integration from minus infinity to plus infinity into three pieces. Minus infinity to minus a, so only negative numbers here, negative x values here. Minus a to b, this straddles both negative and positive values, and b to infinity. So let's call these three pieces I minus, the one over both negative and positive values, I0, the one where the domain of integration includes 0, and I plus. Now on I plus, what you do is you carry out a substitution z equals b square by x. The reason why you want to do that is, firstly, dx of course becomes minus b square by z square dz. It's a pretty straightforward substitution, and I plus becomes minus b square by z square dz coming from dx, and f of course is f of x, but x is b square by z, so f of b square by z. The important thing about doing this is that the limits what happens to the limits? B square by b is a lower limit, and that's of course b, and b square by infinity is the upper limit, which is of course now 0. So this, with a switch in the order of the limits, becomes 0 to b square by z square, f of b square by z square dz. In I minus, you carry out a very similar substitution. Substitute z equal to a square by x, and this gives ultimately boils down to something very similar, but the integral is now from minus a to 0. So your actual integral was one where the sum of these three terms, this has become, after the substitution, an integral from minus a to 0. This has become an integral from 0 to b, and this of course can be split up into two integrals, one from minus a to 0, the other from 0 to b, and if you club them together, this is what you end up with. So this is a way in which, by using substitution, you have reduced your domain of integration, which was from minus infinity to plus infinity, to a finite domain, minus a to b. In fact, you have two different integrands here. One takes over from minus a to 0, the other from 0 to b. One particularly important thing is, you can of course calculate these things which are over finite intervals by standard numerical methods, maybe Simpson's, maybe trapezoidal, maybe Gauss quadrature, whatever. One very simple thing which is very well adapted to Gauss quadrature is, okay, before we go there, let's just take a look at the fact that it might look like there is a problem here, because at the upper limit here you have 0, here you have a lower limit of 0. At the end points, you have a 1 by x square sitting in both of these extra pieces, and 1 by x square should diverge as x goes to 0. However, you have to realize that when x goes to 0, the argument of f here, a square by x, goes to infinity, either negative infinity as x approaches 0 from the negative side here, or positive infinity as x approaches 0 from the positive side here. In both cases, let me remind you that the integral exists only if the function dies out rapidly enough as its argument goes to plus minus infinity. So frankly, the fact that there is an x going to, there is a 1 by x square sitting here, that should not give us any trouble at the point x equal to 0, because the divergence due to a square by x square is actually cancelled by a stronger divergence which must come from this function. However, if you are using a numerical method, you have to be very careful, because when you are using a numerical method, you will end up with a result like f of a square by 0 times a square by 0 square, whichever is calculated first, the computer is definitely going to complain about a division by 0. So if the integrand is evaluated at x equal to 0, it will lead to a 0 division error. So this, you have to remember that although x equal to 0 does not pose a real problem in this calculation, provided of course the function dies out rapidly enough at infinity for the integral to be finite, in a numerical method you have to take care to avoid x equal to 0, because if you get a 0 division error, your computation would end then and there. So the numerical algorithm must be chosen so that the evaluation of the integrand at x equal to 0 is avoided. Now one simple case here is, if you choose a and b both to be 1, then this becomes minus 1 to 1, this becomes 0 to 1, and the integrand becomes the same in both cases, and you end up with a particularly simple form. And what is even more interesting is that this is precisely the form where the Gauss integration can be done trivially, right, even without a change of variables. This is the basic Gauss-Legendre integration setup, and your Gauss-Legendre calculation can be done very, very easily here. Okay, so this is basically one of the ways in which you can change an infinite interval integral, an integral over the entire real line, into an integral over a finite piece. This is not the only way in which you can do it, And this particular way has this issue with it, that you have to make sure that the integrand is not evaluated at x equal to 0 here. Okay, so if you are using Gauss quadrature, which is what this is particularly suited for, being an integral from -1 to +1, you have to ensure that you are not evaluating the function at x equal to 0 as always, and that is why you should choose even order Gauss quadrature, because odd order Gauss quadratures actually involve, among other points, the point x equal to 0 as a node. So odd order Gauss quadrature is something you cannot use with this, but well, you can definitely use even order Gauss quadrature for this. There are other ways. You can carry out an integral like this. You can break this up from -infinity to 0 plus 0 to infinity, and then see that this essentially becomes the integral from 0 to infinity of f of x plus f of minus x dx. This is a familiar old substitution of variable trick that you know, or you should know, from your class 12 days. And here, if you substitute x equal to 1 minus t by t, again a substitution designed to ensure that the limits become finite. So at t equal to 0, so t is of course 1 by 1 plus x. So at x equal to 0, which is the lower limit here, t is 1, and x equal to infinity, t is 0. dx dt is dt by t square, pretty straightforward to calculate, because x is of course 1 by t minus 1, but there is a minus sign here, sorry, I messed that out. Dx dt is minus 1 by t square, so dx is minus 1 by dt minus dt by t square. If you take all that into account, use the minus sign to flip the order of the limits, you end up with this result. So this is a form once again where once again the t equal to 0 should not be a problem, and with Gauss quadrature it's never a problem as long as you avoid calculating the integrand at t equal to 0. With Gauss quadrature that's never a problem, because Gauss quadrature never evaluates the integral at the endpoints. But if you are using standard trapezoidal or Simpson, you will run into trouble with this particular version. So you have to choose your integration algorithm accordingly. The previous formula involved a different substitution. This is particularly well suited for Gauss quadrature, but Gauss quadrature with even order only. This formula is also well suited for Gauss quadrature. Of course, you have to shift your variables by the standard method that we discussed when we were talking about Gauss quadrature to use this. And the only point is, with Gauss quadrature this is always safe because you never evaluate the integrand at the endpoints. And this is exactly what the SciPy quad function uses to handle infinite limits. So whenever you calculate an integral of a function using SciPy quad and supply infinite intervals, this actually is the algorithm or a derivative depending, or a related result depending on whether both limits are infinite or only one is infinite. That kind of thing is used in SciPy quad. And the advantage with SciPy quad is that there you use Gauss-Kronrod quadrature, if you remember, and Gauss-Kronrod actually carries out two different orders of integration, n and 2n plus 1. Of course, the second one is bound to be odd order. So if you just use the quad function on the previous calculation, previous result, you are bound to get a zero division error. This one avoids that, because no matter what the order, Gauss or Gauss-Kronrod, you never evaluate the integrand at the end point. So this one, where the trouble is at the end point, is safe from that. Now this may not be the only possible way of changing an, in fact may not be is wrong, this is definitely not the only possible way of changing infinite limits to finite ones, and this may not be the best way for an arbitrary function. So sometimes, depending on which function you are integrating, you may have to change the algorithm which you are using. That is, the substitution you are making to change the interval into a finite one. But this actually shows you the basic idea. Now, it is a bit more difficult to handle the other kind of improper integral, where the integrand diverges, especially if it diverges in the middle of the interval. Sometimes just avoiding that integration, that particular point, choosing an algorithm where the value is never calculated at that point, may be enough to give you a reasonably good result, but that's often not the case. Okay, so this is not there is no real panacea to this. You cannot expect just one formula which will work everywhere. You have to treat them case by case. So just to illustrate the basic ideas here, let me stop the presentation and go over to Python itself. So I've already imported numpy as np for you, and I've also imported scipy.integrate as si. Just to illustrate the basic idea that we are talking about here, I'm going to talk about a very simple integral over the entire real line. Is integral of e to the minus x square. So first let's define the function using the lambda keyword that we have learned. We define is that now let's to show you that you don't have to worry about much of this if you are using scipy.integrate. The quad function can do this calculation pretty easily. Remember, you have to call it with si being the name of scipy.integrate submodule for us here. You call it with si.quad. The first argument has to be the name of the function, then the lower limit, which is minus np.inf, that's for the infinity. By the way, depending on your version of scipy, np.inft might still work, might also work, but np.inf works almost always, not almost always, always. So this is the call, and as you know, it returns two things: a numerical estimate of the value and a numerical estimate of the error, and this is the value that you are going to get. So just to see whether this is right, I will extract the 0th element from this tuple that si.quad has returned to me. Just to remind you, underscore simply recovers the last result. So underscore really is nothing but this tuple here. You take the 0th element, which is the answer, and you know the answer should be root pi. So let's square this and divide by np.pi and see. This of course is pretty close to 1. In fact, this is 1 for all practical machine dependent reason. So this has done a pretty good job of it. Instead of doing this, could we have used our results? So this of course avoids any of the theory that we have talked about, simply because this theory is taken care of by the quad function itself. However, let me just remind you that we could have calculated this integral using Gauss quadrature, and so let me first define a new function using, which is nothing but our integrand, which maps x to plus so this is my function. Now can I use si.quad on that? Well, of course, remember, for si.quad here I cannot use the same minus infinity to plus infinity limit. What I nearly need to do is minus 1 to plus 1, and I should expect a perfectly nice result. Horror of horrors, it doesn't work. It gives you a zero division error. But just to remind you that this is exactly what we warned you against. This function has a divergence, well, not really a divergence, but problem at x equal to 0 because of both the 1 by x, the argument of f that has to be calculated, also because you have to divide it by x square, and that will cause a zero deviation error if you were ever to try to evaluate this function at x equal to 0. Quad uses Gauss-Kronrod quadrature, and that either in the Gauss or in the Kronrod evaluates the function at x equal to 0. So, you cannot use this particular prescription in conjunction with the quad argument. Can use it, not this one, but the other formula that we talked about in conjunction with the quad, but there the limits will be 0 to 1, and frankly doing that is really rather useless because that's exactly what quad does internally. When you are supposed to integrate a function f from minus infinity to plus infinity, it changes the integrand and does the integral from 0 to infinity according to the second formula that we talked about. But this of course does not mean that the result about integrating this function f of x plus f of 1 by x square from minus 1 to plus 1 is useless. It's actually pretty useful if you are not using the quad function. What you could do is, for example, integrate this using Gauss quadrature, maybe 32-point Gauss quadrature. Let's see what happens. Remember, for this what we need are the nodes and the weights, and for this I already have the loads and weights, nodes and weights of 32-point Gauss quadrature written in a file. The file name most probably, as I remember, is gauss32.dat. Okay, the file name was correct, otherwise I would have got an error here. And just to remind you, if you just take a look at one row of this, the first entry here is a serial number, the second entry is a weight, the third entry are the nodes, the positions where you need to calculate. So, what you need is to slice up the array V so that you get the 1th column, the second column really. And this you can get by just slicing, by taking all the row indices. That's why it's from the beginning till the end, just a plain colon, no beginning, no end specified, means all of it. And the second index, the one axis index has to be 1. This is how you pick the second column or the 1th column. The nodes, that was the weights, nodes can be picked by exactly the same method. There is a 2th column here. So, I now have the nodes and weights ready, and what I need to do is simply calculate this sum. This exactly is how you calculate, using Gauss quadrature, the integral of the function g from minus 1 to plus 1. If you do not remember this, please look up the video that I had made on Gauss quadrature before, and this is the value you are getting. Of course, this is not as accurate as what we had figured out earlier. If you see, square of this divided by pi is not exactly 1, pretty close, but not. That one had 9s all the way. This one has only 1, 2, 3, 4, 5, 6 9s, and then an 8. Of course, this is still accurate to within 10 to the minus 7, pretty good, I would say. But that one is even more accurate simply because that uses adaptive Gauss-Kronrod quadrature. If it does not use as high an order as 32, it uses only 7 and 15. But then if the error turns out to be too big, it divides the interval into smaller pieces and keeps on repeating this until the error becomes very, very small. That of course is something we have already described earlier in talking about Gauss-Kronrod quadrature and the quad function. So this basically is how you handle improper integrals, at least integrals over infinite intervals. As I said, integrals with divergences in the middle of the interval are usually trickier. Very often choosing algorithms which avoid that point might work, especially if the integral, if despite being improper the integral is still well defined mathematically. There is one very important thing that I must emphasize here, and this is why just because you have a computer you cannot ignore the underlying mathematics. If you are trying to integrate a function, an integrand which diverges somewhere in the interval, and the improper integral in the limit of in the sense of the properly taken limit does not exist, then there is every chance that a blind application of the numerical method by avoiding that point of divergence might give you a completely nonsensical result, might give you a result, some number which has nothing to do with the final answer. In fact, the final answer does not exist, but your calculation may end up giving you a value, and you may end up believing the value. So even if you are using a computer to do calculations, please remember understanding the underlying mathematics is always very important. This of course is not a statement only about a numerical evaluation of improper integrals. This is a statement which is true for all applications of numerical mathematics. So any numerical computation, just blindly using a computer is not good enough. You have to also understand what's going on really behind the scenes.